Well, thanks to Era and Hassan for giving me the opportunity to introduce the speaker today. Uh, well, so today's speaker, I think the Kent seminar series is Xian Xie. He's a graduate student working with me now, and then he obtained his, just a little bit about him, he obtained his bachelor's degree in civil engineering from Tsinghua University, China in 2013, and he obtained the top honor from the department, the top student in his year. And he currently is now pursuing 2 master's degrees and also with a plan of continuing to PhD. He is pursuing both a master's degree in civil engineering in our department as well as in the applied mathematics department. And his research has been working with me on a number of topics, and his major area is generally in logistics systems and also on traffic control and network reliability. So today, he actually is going to talk about some of the recent work that we have been doing. It's about actually when we are designing, he's going to talk more about it, but just a little bit flavor is that actually we are designing service systems, and then we are trying to locate facilities, and then facilities themselves may be subject to disasters, and then the disasters may be correlated, and how do we deal with those complicated situations? So, Sia, please.
Hello, everyone. So the professor has introduced my background. Today I will present my recent work. The topic is reliable facility location design under correlated facility disruptions. This is a joint work with Kun An and my advisor, Professor Yanfeng Yang. My presentation today has 4 parts. I will first give you an introduction of this study. Then the methodology will be presented. Next, I will show you some numerical examples to demonstrate our methodology. Finally, I will draw the conclusions. I'll first go into the introduction part and give you the basic ideas, motivations, and backgrounds of this study. The traditional facility location models have been studied for a long time. In this problem, we are given a network with a bunch of customers. Each customer has a demand to be served. We are trying to build facilities in the network to provide service to all these customers. The main constraint is to satisfy the demand of all these customers, and the objective is to balance between the facility construction cost and transportation cost. It's easy to imagine that if we build more facilities, the facility cost will be increased. At the same time, we have more facilities, the customers may have more options, and the transportation cost for them to visit a nearby facility may be reduced. So when this increases, this will be reduced. We should balance between these 2 components. Most of the traditional models assume that any facility is functioning from the time when it was built. But to be realistic, the facilities may be subject to disruptions. That means they are not always available. For example, if there is natural disaster such as earthquake, hurricane happening, then a facility may be totally destroyed by the disaster. It no longer works, or the way or route to these facilities may be cut off by the disaster. Then this facility may become available as well. Similarly, if some accident such as power outage happens, the facilities may require these powers or the materials to work. If the power outage happens, the facilities themselves may no longer be able to provide service, so the facilities are disrupted. In addition, some human factors could lead to the facility disruptions as well. A quite intuitive example is the strikes. So if the if the workers in the facility refuse to work, definitely the functionality of the facility will be affected. So all these three examples show that facility disruptions are quite common in our real-world facility systems. And these possible disruptions will have a huge impact on the facility location design. Intuitively, if this facility is disrupted, it no longer exists in this network, then the customers originally assigned to this facility will have to seek more distant facilities or even lose service. See this example. The customer will first go to the closest facility for service. Then if this one is disrupted, the customer may have to go to another one and pay higher transportation cost. In the worst case, if all the facilities within this reachable distance fail, then this customer has to give up service, and it has to pay the penalty for losing service. Therefore, with consideration of the facility disruptions, the system planning decisions may be totally changed compared to the situation when there's no disruption. As you can see, these two customers are assigned to two other facilities, and this customer may give up service. So when there's correlation, we should not only balance between the facility cost and the transportation cost. We should also balance between the normal scenarios and the disruption scenarios. Still take this example. If we only focus on the normal scenario, the optimal decisions may choose to build a facility here. But what happens if this location is subject to disruption with high probability? Then that means with high probability, these customers will pay higher cost, either transportation or the penalty cost. Then the cost for this scenario will be pretty high. If we ignore this one, the system design solution might be suboptimal. There are already many studies dealing with the disruption issue, but most of these models have the assumption that disruptions are independent. However, in reality, this is not always the case, as I will show you next. Consider a facility system. This is a power outage. Then the facility in this region are subject to simultaneous disruptions, and they perform a positive correlation with each other. That means if one facility is disrupted, the probability for other facility to be disrupted will be relatively high. Consider another network where several factories share one power plant. Then if this power plant is disrupted, all these factories will be affected simultaneously. So these facilities also exhibit positive correlation. On the other hand, negative correlation can be observed in reality as well. In this picture, we have two factories competing for the material. Then if one of the factories fail, the other factory will obtain more material, and the possibility for this factory to be disrupted will be smaller. So somehow these two facilities perform a negative correlation. In most real-world cases, such as the natural disaster, the correlation commonly exists with both positive and negative correlation pattern involved. So these cases all show that correlation is also a common issue in real-world facility systems. Now I would like to discuss more about the disruption correlations. Basically, we categorize the correlation into two patterns. The first one we call it shared hazard pattern. In this pattern, multiple facilities are subject to shared impacts. As shown in this picture, this is the effect of Hurricane Sandy. You can see the regions with the same color are attacked by the hurricane simultaneously, so facilities within the same regions may be subject to the shared impact from the hurricane. In this pattern, the disruption occurred directly at these facilities. And the reason why there is correlation is that because several facilities may be disrupted simultaneously, and we cannot treat them independently or separately. So there's correlation in this system. The second pattern we call it support failure pattern. In this pattern, facilities themselves are still working, but they require some external support. Take this for example. We have an area which is partitioned by 3 rivers into several subregions. Then, for a customer to go from one region to a facility in another region, it has to pass through the bridge. Then, if this bridge is blocked or disrupted, the customer may seek another path, or it may not be able to reach the facility. So here, the bridge can be treated as the support to this facility, and the disruption of this support will affect the reachability or functionality of the facility. So we have several facilities and we have some external support which provide support to these facilities. And in this pattern, the disruptions occur at this support. And the reason why there's correlation is that because these two facilities share one common support. Then, if this support is disrupted, it will affect both of the two facilities. And these facilities are correlated with each other. Similarly, these two are also correlated. So we have shown that correlation is common in reality. The next question is, why should we consider correlation in our system design? Can we just ignore them? The following toy example will show you the answer. Here we have a simple network with one customer and 2 facilities. The distance are 10 and 20 respectively. If there's no disruption, the customer will serve by A because the distance is smaller and the cost will be 10. If there's independent disruptions, we assume that facility A and B both fail with probability 0.5. Then if facility A is functioning, the customer will be served by A with probability 0.5. Then if A is disrupted and B is functioning, the probability is 0.25. The customer will be served by B and the cost is 20. In the worst case, if both A and B are disrupted, the customer has to pay the penalty 100 with probability 0.25. And the total cost is 35. Further, we assume that the disruption is correlated with each other, as listed in this table. Here, for example, the situation when A is functioning and B is disrupted has a probability 0.4. And you can observe that the marginal probability for A or B to be disrupted is 0.5, which is equal to the values in this case. But when there's correlation, the total cost is 23, which is quite different from the value 35. So this comparison tells us that if there's correlation involved and we ignore the correlation, we will get a quite inaccurate cost evaluation, which will further affect the quality of our system design. We have claimed that correlation is quite common and is a significant issue that needs to be addressed. But as far as we know, only very limited work has been done in this area to deal with correlation issues. There are several associated challenges. The first challenge is the representation of this correlation. Since the facilities are correlated with each other, we cannot simply decouple the system into individual facilities. Assume we have a system with n facilities. If these facilities are independent to each other, then what we can do is that we study the state of each facility, and we combine the state of all facilities to get the system state. But if the facilities are correlated with each other, we should consider all these scenarios. Here, each scenario corresponds to one row. In each scenario, each facility is either functioning or be disrupted. Then to calculate the total system cost, we have to compute the cost in each scenario and finally calculate the expectation value across all these scenarios. The total number of possible scenarios is 2 to the power of n, which is a huge number when n is relatively large. So this means usually it's impossible to simply enumerate all these scenarios. The second challenge is how we can optimize the facility locations. From the modeling side, as we show in this example, with the given facility locations, it's extremely complex to evaluate the system cost because we have an exponential size of scenarios. Then, if we want to optimize the facility locations from a large number of candidate locations, the problem will be even more complex to formulate and model. From the solving side, after we built the model for this facility location design problem, as you can imagine, it will be quite complex, and the real-world applications are usually large scale. So how to solve the model efficiently will be a challenging work. Now I will introduce the methodologies we developed to handle these challenges. This slide shows the overall framework of our methodology. Given the correlation of either the shared hazard pattern or the support failure pattern, we first represent it in a probabilistic representation. Then from the probabilistic representation, we built a unified station structure representation using either the decomposition all the transformation techniques. These representations and techniques will be explained later. Then, based on the station structure representation, we formulate the location design problem into an optimization model. Finally, we design several customized solution approaches to solve this model effectively and get the final location design solution. The first part of our methodology is to represent the correlation using some mathematical probabilistic form. Here we use 3 typical probabilistic representations. The first one is a scenario-based one. This picture shows the scenario-based state of a facility system. We have a facility consisting of 3 facilities. Each scenario corresponds to a specific time period. In this time period, some facilities are functioning while the other facilities are disrupted. And the scenario probability is defined as this time length, the ratio of this time length to the whole time length. The second one is the conditional based representation. Similarly, we take this picture for example. The conditional probability is defined as the probability for facility 3 to be disrupted based on the disruption of facility 1 and 2. So basically, it's the ratio of this time length to this time length. The last representation is a marginal-based representation. This one is similar to the scenario representation. The difference is that here, during a time period, we know that some facilities are disrupted, but we have no information of the others. So this is the reason why we call it marginal, because we only know the state of these 2. Then, to unify these 3 representations, we develop the pairwise transformations between them. 6 sets of equations are implemented for the probability transformation. I won't go into the mathematical details, but to give you a big picture, this framework is a preparation step of our methodology. And given this framework, given the correlation description, we can represent it in any of these 3 probabilistic forms. And this one will be used later. Now we have represented the correlation in a mathematical form, but still it cannot be directly used for the facility location design. Therefore, we further propose a station structure representation to represent the correlation. This idea is first introduced in a reference. Basically, we augment the original facility system by adding an additional layer of stations. Then we properly connect these stations to these facilities. We require that a facility is functioning if and only if at least one of the connected stations is functioning. For example, if this facility is disrupted, then that means both these 2 stations should be disrupted. Otherwise, if this one is functioning, then it can kind of provide support to this facility, and this facility is still able to work. Moreover, we assume that the station disruptions are independent. So the basic idea of this representation is to use the independent station disruption to capture the correlated facility disruptions. Then we can focus on the station layers and model with independent disruptions, which has been studied intensively. We use the station structure representation for two purposes. The first one is to represent the correlation of the both patterns we mentioned before. Suppose we are given the correlation of the support failure pattern. Here, to recall, we have several facilities and we have some external supports of these facilities. These supports are subject to disruptions. Then intuitively, we simply interpret this support as stations, and we connect the stations with the facilities just as what we have in the reality. So in this system, a facility is functioning if and only if one of the support can provide support to the facility. So the two systems are same in the behaviors. On the other hand, if we are given the correlation of the shared hazard pattern, now we don't have explicit support. This case is less intuitive, but we proved in this paper that we can decompose this system into a similar facility station network. Here the decomposition means that the correlation within the facilities can be captured by the stations, by the disruption of the stations, as we mentioned in the previous slide. The second purpose of this representation is to help develop the model. Since now the correlated disruption of facilities are captured by the independent failures of stations, by proving that this system and this system are equivalent in evaluating the system cost, we can simply model with the stations, because the stations, the state of the stations can represent the state of the facilities. And since they are independent to each other, we only need to deal with independence issues, and we can escape from the complexity of the correlation. This slide shows the details for the decomposition from this correlation into the station structure. From the three probabilistic representations, we want to build the station structure. So basically, we develop three sets of equations to transfer each of the three probabilistic representations to the station structure representation. Then this framework, together with the previous framework for the pairwise transformations between these three, we are guaranteed. Oh, one more statement. We have proved that this decomposition always exists, and is unique. So we are guaranteed to get a unique station structure given any correlation description in a reality. Now we have obtained the station structure. We are ready for developing a model based on it. This model has several components. We have several candidate locations. Each location has a fixed construction cost. We have multiple supporting stations. These stations are subject to independent disruptions. And we have multiple customer demand points. And each demand point has a maximum backup level, maximum number of backup level, and the penalty cost for losing service. The decisions include the facility number and locations, as well as the assignment of customers to facilities. Major part of the optimization model is listed here. We are minimizing the total expected system cost, including the fixed cost and the transportation and penalty cost. There are several constraints. We call it facility choice. This means a customer can be only assigned to a location if there's a facility there. And we have some other constraints, say, related to the stations, the backup levels, and the probabilities of the assignment. And since we notice that we have nonlinear terms in the model, we develop a linearization constraint to transfer the model into a linear mixed integer mathematical model. As you can see, this model involves a large number of integer variables, which makes it extremely complex to solve. We have tried to use commercial solvers like Cplex to solve it, but usually the computation time is unbearable and the final optimality gap is too large. So to hedge against this complexity, we develop the Lagrangian relaxation algorithm based on branch and bound framework. And also we have some approximation algorithms to solve the subproblems which comes from the relaxation. This algorithm tends to perform quite well. We can solve most real-world cases. For example, we are able to solve a case with 50 candidate locations and 100 stations with 4 to 5 backup levels. The final gap is around 3%, and we can solve it within 2 hours. From now on, I will show you some numerical case studies to illustrate and demonstrate our methodology. The first case is the location design in the Illinois railroad network. Here, the whole area is partitioned by the rail segments into multiple regions. Each region represents a candidate location as well as a demand point. We are trying to build facilities in this network to serve all this demand. For a demand to go from one point to another, similarly, it has to pass through some access point in a rail segment, and this access point are assumed to be subject to disruptions. So this access point can be treated as support to the facilities, and through this case, we show how our methodology handles the correlation of the support failure pattern. We run multiple cases in this network with 3 solution approaches. First, we use Cplex to solve it directly. Then we use Lagrangian relaxation plus branch and bound plus Cplex for each subproblem. And finally, we use Lagrangian relaxation plus branch and bound plus approximation algorithm for each subproblem. The final solution statistics are summarized in this table. We have various parameter settings. For example, the the access point disruption probabilities are different in different cases, and we vary the number of maximum backup level to test its effect. From the solution, we can see that when the disruption probabilities are different, the facility location decisions are different, and also the total system costs are different. But the number of R doesn't have any effect on the locations. Then we compare these three solution approaches with the simplex directly. In some cases, we are not able to reach true optimality, and the computation time is relatively long. Then with the second approach, we are able to get optimal solution for all the cases. But as you can see, the computational time is around 1 hour or 2 hours. Now let's look at the third approach. We can get optimal solution for all the cases, and the computation time is even few seconds. That means this approach is the best approach.
This is our approach, right?
Yeah.
Yeah, because the other ones are benchmarked to compare.
Yes. Then these four pictures shows the decisions of the model in one case. Here we built 3 facility locations in a network, and each picture shows the customer assignment plans at different backup level. So at level 1, this is the first priority choice of each customer. So for example, this customer will first choose to go to this facility through this segment. Then in the second level, it will go to another facility through another station. The second case we study is a grid network consisting of 16 locations, and an earthquake is assumed to happen at location 1. Then the earthquake spread out to the other locations. In this case, the probability correlation involved, and since the locations themselves are subject to disruptions, this is a correlation of the shared hazard pattern. So as suggested by the methodology, we first decompose the correlation into a station structure. Here, we have 10 stations. Which station is connected to multiple facilities, and these two systems are equivalent. Then based on the facility station system, we build the model and solve it. We have run 4 different cases. The first one is with correlation and the demand is homogeneous. The second one is without correlation and with homogeneous demand. The third one is with correlation but the demand is heterogeneous. The demand is centered. The demand in the centered area is higher than the demand in the outer area. The last case is without correlation and with heterogeneous demand. The solution statistics are summarized in the table. First, we notice that all the 3 cases can be solved in few minutes. So this again demonstrates the efficiency of our methodology. Then we compare the cases with and without correlation. We can see that the facility locations are different and the system costs are also different. That means if there's correlation, we have to incorporate it. Otherwise, we will get a totally different location design solution. Then we compare the case with homogeneous and heterogeneous demand, as shown in picture A and picture C. Generally, the numbers of facilities for the heterogeneous demand is fewer than the case with homogeneous demand, because now demands are centered in this area, and for example, we don't need these facilities to reduce the facility cost. Similarly, pattern can be observed when we compare figure B and figure D. We have only 2 facilities with heterogeneous demand, but 4 with homogeneous demand. Also, I want to mention that when we compare figure A and figure B, figure A is with correlation, figure B is without correlation. The facilities in figure A are more scattered to hedge against the correlation, because when there's correlation, these facilities might be disrupted simultaneously with a high probability. If you build both of them, then that means if this one is disrupted, this one is possible to be disrupted as well. Then what's the meaning of build a facility here? So in the case with correlation, we no longer build a facility here. Instead, we move the facility to this place. The final case we run is a flooding case. In this case, we use the same grid network, but here we have a river across this region, and we assume that the flooding can happen at any of this place. Then after it happens, it can spread out in all directions. Then we also give the scenario-based facility disruptions where the correlation is involved. We built the station structure based on our decomposition technique.
No, there's a negative correlation.
Yeah. So in the earthquake case, the correlation is positive, but here in the flooding case, the correlation can be either positive or negative. For example, if the flooding happens here, then it will spread out in these directions. Then the facility locations in this direction will be positively correlated. But at the same time, if flooding happens here, the pressure will be released, and the possibility for the flooding to happen in this place will be smaller. So then these 2 locations exhibit a negative correlation. Then based on the facility station system, we built the model and solve it. Well, we show the solution statistics, and also we run the 4 different scenarios. So we compare figure A and figure B with correlation and without correlation. Actually, the locations in these 2 cases are identical because all the parameters are said to be symmetric to this river. So compared to the network case, we have exactly the same facility location decisions for the case with correlation and without correlation. The reason is because we have both positive correlation and negative correlation in this system. Then the effect of the positive correlation and negative correlation will cancel out. So that means the correlation in this system is quite weak, and it will have a slight impact on the location design. If we compare figure A and figure C, we can see the same pattern. The number of stations with a heterogeneous demand is smaller than the case with homogeneous demand. Finally, I will conclude the work and talk about some future work. In this study, we developed a methodology for the reliable facility location problem with correlated facility disruptions. We've represented a correlation with several representations. We built the optimization model, and we designed customized algorithms to effectively solve it. Then we used several case studies with real-world context to illustrate and demonstrate our methodology. There are several possible future work. In this study, we assume that the station disruptions are independent. In the future, we may relax the independence assumption and consider correlated station disruptions. Also, if we want to solve even larger cases, we may need to develop more sophisticated algorithms to improve the solving speed. That's my presentation today. Thank you. Any question?
Any questions? Well, no questions? Oh, okay. Yeah.
When you try different algorithms to solve your problem, how can you compare different results? I mean, each method that you use, let's say branch and bound or your complex simplex model, the answers that you get can be different. But which one is the best answer or to problem? Is there any way to compare? I mean, it's hard to see the numbers, but you can explain
Can
it.
you blow it up?
So basically, we have two. We can compare the different approaches with two things. The first one is computation time. The second one is the final optimality gap. So
What is optimal?
optimality gap is the gap between the optimal solution and the best solution we obtain. So if the optimality gap is smaller, that means our solution is better. So for the case, if we use simplex, for some cases, we cannot close the gap.
And what is that gap coming from? I mean, there should be a baseline to the gap too, right? What is your baseline?
Oh, the simplex will automatically give the gap.
Maybe you want to explain how the gap is obtained, even in simplex in general.
Yeah, so basically the simplex will.
Oh, generally, right?
Yeah.
I'll try. Very often the optimization problem, it's very hard to know where the optimum is. It's just so hard, we couldn't know. But then there are ways, even his method, Lagrange relaxation, we are trying to find some theoretical bounds to the optimality. So we know the optimum is somewhere, we don't know. It's somewhere in the cloud. But we are able to obtain some values that we know it's surely larger or smaller than it. We try to these two bounds to push them together. And then wherever we have to stop, that the difference between the two, we know the true optimum is in between. But we try our best to push them to touch that by optimum. But then some methods try, as much as they try, simplex cannot close it, they stop somewhere. We were able, if the problem gets really large, just impossible to close it. but we have been doing a little better than the solvers and stuff. So
which one is important, automatic or time?
Both are important.
we try to be better both ways.
So if you compare the second one and the third one, both of them can get the optimal solution for all the cases. But the third one can finish in few seconds. But the second one requires 1 hour or 2 hours. Then definitely we prefer the third one.
We really try to trash the solvers because that's the industry standard, and then we try to, we can do better by designing our own algorithms. So. Any other questions? Well, if not, then thank you very much for being here. Thank you.